Hey everyone, welcome back to Chem Story. Today we're diving into the different types of chemical reactions in organic chemistry. Understanding how these reactions are classified makes it way easier to follow their mechanisms and to predict what kinds of products you'll get. Whether you're getting ready for a test or just want a better grasp of the big picture, this breakdown is going to help you connect the dots, so let's get started. There are lots of ways to classify chemical reactions, but one of the most helpful is to divide them into two big categories: reactions based on structural changes, and reactions based on mechanisms. Let's start with structural changes. This type of classification is all about how molecules transform during a reaction. The major types include substitution, addition, elimination, rearrangement, acid-base, and oxidation-reduction reactions. Now let's shift gears and look at how reactions are classified based on their mechanisms. This approach focuses on what's actually happening at the molecular level, how bonds break, and how new ones form. There are three major types: polar reactions, radical reactions, and pericyclic reactions. Let's start with polar reactions, also known as ionic reactions. These involve the movement of electrons between two key players, nucleophiles and electrophiles. In nucleophilic reactions, a nucleophile, that's an electron-rich species, donates a pair of electrons to form a new bond. The molecule it attacks is called the substrate, and it acts as an electrophile, meaning it has an electron-deficient site that can accept those donated electrons. Electrophilic reactions work the opposite way. Here, the electrophile, which is an electron-deficient species, accepts an electron pair. Meanwhile, the substrate acts as a nucleophile, donating electrons to form a new bond. These types of reactions are super important in organic chemistry, especially when we talk about nucleophilic substitutions and electrophilic additions. Radical reactions work through a completely different mechanism compared to polar reactions. Instead of moving around pairs of electrons, they involve single electron shifts, which makes the chemistry behave very differently. These reactions usually follow a three-step sequence: initiation, propagation, and termination. Pericyclic reactions involve a concerted flow of electrons in a cyclic transition state and follow rules like the Woodward-Hoffman rules. A classic example is the Diels-Alder reaction, which forms a six-membered ring in one step. Importantly, classifying reactions by structure or by mechanism isn't mutually exclusive. Many reactions fit into both categories. For instance, substitution can be polar or radical, and addition can be electrophilic or nucleophilic. Recognizing this overlap helps us better understand reaction pathways. Now, let's move into the details, starting with substitution reactions. A substitution reaction happens when one functional group in a molecule gets swapped out for another. That means one sigma bond is broken, and a new one is formed in its place. Exactly how this happens depends on the type of substrate and the reaction conditions. Substitution reactions are typically divided into two main types: polar substitution and radical substitution. In polar reactions, the mechanism can vary depending on whether the substitution is nucleophilic or electrophilic. One common example of nucleophilic substitution is when ethyl bromide reacts with hydroxide ion. In this reaction, the hydroxide kicks out the bromine, leading to the formation of ethanol. Another example is nucleophilic aromatic substitution, or SNAR. In this case, fluoronitrobenzene reacts with hydroxide, and the product is nitrophenol. In electrophilic substitution, an electrophile replaces a group in an electron-rich system, like an aromatic ring. These reactions often require a Lewis acid to activate the electrophile. A classic example is bromination of benzene with Br2 and FeBr3, forming bromobenzene. Radical substitution follows a chain mechanism with initiation, propagation, and termination. For example, in cyclohexane chlorination, Cl2 and UV light generate chlorine radicals that react to form chlorocyclohexane. Now, let's move on to addition reactions, where new atoms are added instead of swapped out. Next, let's take a look at addition reactions. These happen when two or more reactants come together to form a single product, what we call an adduct. In most cases, a pi bond is broken, usually from an alkene, alkyne, or carbonyl compound, and two new sigma bonds are formed in its place. Since pi bonds are generally weaker than sigma bonds, This kind of reaction tends to be energetically favorable, which is why addition reactions are so common in organic chemistry. Addition reactions can be grouped into two main types, polar and radical. Polar additions are further split into two categories, electrophilic and nucleophilic, depending on whether the reactive species is donating or accepting an electron pair. In electrophilic addition reactions, an electrophile adds to a carbon-carbon multiple bond, usually a double or triple bond. A classic example is the addition of HBr to an alkene. First, the proton adds to the double bond, creating a carbocation ion intermediate. Then, the bromide ion attacks that carbocation ion, and the overall process follows Markovnikov's rule. A similar thing happens with alkynes. The first molecule of HBr breaks the triple bond, turning the alkyne into an alkene. And if you add more HBr, the reaction keeps going, eventually forming a geminal dihalide, where both bromine atoms end up on the same carbon. Nucleophilic addition reactions are especially important in carbonyl chemistry. A key example is acetal formation, where aldehydes or ketones react with alcohols under acidic conditions to protect carbonyl groups. Radical addition reactions, typically seen in alkenes, follow a stepwise mechanism: initiation, propagation, and termination. A classic case is anti-Markovnikov hydrohalogenation, where HBr adds in the presence of peroxides, reversing the usual regioselectivity. Overall, addition reactions are fundamental tools in organic synthesis, enabling the transformation of unsaturated compounds into more complex molecules. Elimination reactions happen when two substituents are removed from a molecule and a new pi bond is formed. In this process, two atoms or groups that were originally sigma bonded to neighboring carbon atoms get eliminated, and that leads to the formation of a double or even a triple bond. These reactions can follow either a one-step or a two-step mechanism, depending on the substrate and the reaction conditions. Since elimination involves removing atoms or functional groups, it's often thought of as the reverse of an addition reaction. Elimination reactions are generally divided into three types: E1, E2, and E1CB. E1 reactions happen in two steps. First, the leaving group leaves, forming a carbocation ion. Then, a base removes a nearby proton, leading to pi bond formation. This mechanism works best when the carbocation ion can be stabilized, like in tertiary alkyl halides or alcohols under acidic conditions. E2 reactions are concerted. The base removes a proton at the same time the leaving group departs. It requires anti-periplanar geometry, and it's common with primary or secondary alkyl halides when a strong base is used. E1CB reactions go through a carbanion intermediate. They usually occur when the leaving group is poor, but the beta hydrogen is acidic, often due to a nearby carbonyl group. Elimination reactions are essential in synthesis, especially for making alkenes and alkynes, and they're often used alongside substitution reactions to fine-tune molecular structure. Rearrangement reactions happen when atoms or groups shift positions within a molecule, forming a new isomer without adding or removing atoms. These shifts usually create a more stable structure, which makes them especially useful in organic synthesis. One common type is the 1,2 rearrangement, where a group moves from one carbon to a neighboring carbon. This often happens during SN1 or E1 reactions, when a carbocation forms and rearranges to become more stable. Another important type is the sigmatropic rearrangement, a pericyclic reaction where sigma bonds shift within a conjugated pi system. Famous examples include the Cope and Claisen rearrangements, which happen in a single concerted step. Acid-base reactions are some of the most fundamental processes in chemistry. In simple terms, an acid donates protons or accepts electrons, while a base accepts protons or donates electrons. These reactions can be described using three major theories: the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. Let's start with the Arrhenius definition. It says that acids are substances that increase the concentration of H+ in water, and bases are substances that increase the concentration of OH-. A classic example is a neutralization reaction, where H+ from the acid reacts with OH- from the base to form water. The Bronsted-Lowry definition takes this idea a step further. It defines acids as proton donors and bases as proton acceptors. Unlike the Arrhenius model, it doesn't require water as the solvent. That means it works in non-aqueous solutions too, which makes it much more useful in organic chemistry. The Lewis acid-base definition takes an even broader approach. Here, a Lewis acid is something that accepts an electron pair, and a Lewis base donates an electron pair to form a new covalent bond. This model goes beyond proton transfer and helps explain a wide range of organic and inorganic reactions. Understanding these different acid-base concepts is super helpful because it lets you predict reactivity, reaction mechanisms, and how molecules interact, both in organic and inorganic chemistry. Now, let's talk about another fundamental concept: oxidation and reduction. At the core, these reactions are all about tracking electron movement through changes in oxidation states. Oxidation means increasing the oxidation number by losing electrons. Reduction does the opposite. It lowers the oxidation number by gaining electrons. One way to figure out whether a reaction involves oxidation or reduction is by looking at how the bonds change. When a carbon atom forms a new bond with something more electronegative, like oxygen, nitrogen, or a halogen, it loses electron density. That means it's being oxidized. On the flip side, if that same carbon forms more CH bonds, it's gaining electrons, and that counts as reduction. You can also spot oxidation-reduction trends in hydrocarbon compounds. As you move from an alkane to an alkene, and then to an alkyne, the oxidation number of carbon increases because pi bonds are replacing CH bonds along the way. You'll see a similar trend when it comes to CO bond formation. As a molecule goes from an alcohol to an aldehyde or ketone, and then to a carboxylic acid, the oxidation state of carbon keeps increasing. Recognizing patterns like these is super helpful when you're trying to predict how molecules will behave in different reactions. And with that, we've officially covered the major types of organic reactions. Hope this breakdown helped you connect the dots and see the bigger picture. Thanks for watching, and I'll see you in the next one.